domain, did you get the domain of this one? Is everything. And the range greater than or equal to 0. Domain greater than or equal to -2, and the range y is greater than or equal to 0. And here, there are asymptotes. Oh, I use red pen. Asymptotes there and there. So your domain is that x cannot equal -1, and your range is that y cannot equal 0. Now, historically, if we think back to what you started learning back in kindergarten in grade 1, one of the first things you learned how to do was to add and subtract. And then like grade 2 and 3, they added multiplying and dividing. I think they have a thing in grade 2, you're not supposed to multiply past your 5 times table. And then grade 3, they extended a little, you know, it's like, yeah, that kid that learned 6 times 6 early, it's ruined for life. But they extended a little bit each time. And then you get to, well, probably sometime in middle school where they introduced variables, which at that time you were like, we're adding letters now, right? You're adding variables together and you're multiplying variables. And then you...
At least those letters at that point weren't actual numbers. They were just stand-in. And now
And then we've added functions like sine and cosine. We have to multiply those, you get sine squared. So we've been keep adding things that you have to add, subtract, multiply, and divide. That's never gone away since the beginning of school till now. And the idea is, well, what haven't we added, subtracted, multiplied, and divided yet? We haven't done graphs. So today we're going to add graphs, subtract graphs, multiply graphs, and divide graphs. And it's not that crazy hard. But we'll start with an adding one. Graphs below show 2 functions. Function A in red is college enrollment, and B is university enrollment. And someone says, I would like a graph that shows the total of everybody enrolled in post-secondary. So in 2004, does it make sense that if 6 million were in college and just over 10 million in university, that in 2004, combined, you had just over 16 million in both of them. And same thing if 2005 is a tiny bit more. 2006, we're almost at 17 million there. 2007, I think we would have just gone over 17 million. And then for sure, in 2008, we could join that up. And for adding graphs, we just add the y values. Excuse me. And it's not that crazy. And we're going to find that this pattern happens with all kinds of math with graphs. If you want to subtract graphs, you subtract the y values. Multiply graphs, multiply the y values. Sometimes you have, like in this example and the next example, they have a situation. It makes sense that if this is how much and I wanted to find a total, I would just add my y values. The year doesn't change. Your x value doesn't change. Just the total changes. So in our second example, it's a similar idea. They're looking at stopping distance of a car. If you want to slam on your brakes and stop, it takes a certain distance because, I mean, they could probably design cars that are not very good for you that stop instantaneously. You touch your brake and there is like stakes that go straight down into the ground and your car instantaneously stops. And you just slam into your seatbelt, and it would be very, very uncomfortable.
And then from behind.
Well, and the person from behind, but you would stay there. That actually, if crash from behind probably wouldn't give you whiplash, because that car would just, you're staked in the ground, you're just staying there. that probably wouldn't be very good. So instead, what happens is you slam on your brakes and your tires lock and you skid for a bit, and it's still pretty significant, but it's not instantaneous. And the faster you're going, this is what this red is saying, the faster you're going, like if you're going 100 kilometers per hour, it's saying that you will travel about 90 meters before you stop. There's another thing that affects how you stop, which is this reaction time. So for example, if you're driving and you see something jump out onto the road ahead of you and you decide to slam on your brakes, there's a moment where you go and slam on your brakes. But in that breathing in, screaming a little bit, and then slamming your foot on the brakes, that takes a little bit of time. And in that tiny little bit of time, your car doesn't just decide, oh, I'm not going to go forward while you're making a decision. It drives forward a little bit. So apparently, if you're going 100 kilometers an hour and you're really quick at reacting, you will travel 20 meters before you even touch the brakes. Does it make sense that if it took you 90 meters to stop in total, and it took 20 meters to react, that it would be 70 meters of skidding? So, up at the top here, they've got an equation. They've got stopping distance, which I'm going to put a red box around. That's my red graph. Reaction time distance, that's my blue graph. And we want to draw the graph of the braking distance. I'm going to call that B. I'm going to call this R. And I'm going to call this S. So we've got the following equation right now. We've got S equals R plus B. And if I wanted to rearrange this to get the braking distance by itself, oops, sorry, get B by itself, I'd have to subtract the R to the other side. And so we're subtracting. And what's the idea of subtracting? If we're subtracting graphs, again, you just subtract the y values. So we can go through this all the way through. We can say, okay, here at 80, we've got about 58 minus 16, which would be about 42. And we could do this all the way through. We got about 35 minus 12, about 23. 20 minus 8 would be 12. 9 minus 4 would be about 5. Ooh, I like this one. I like this situation right here. You are in a parked car. Something jumps out in front of you and you react. During that reaction, your car does not move. You slam on the brakes. Your car does not move, and your total stopping distance is still 0. That's what would be represented by this point, where everything is 0. Yeah, makes me think of YouTube videos where people show you're driving up behind a tow truck that's towing a semi backwards, and someone, have you ever seen these ones where someone's sleeping in the front seat? And then you just start screaming and they wake up and they see, that's not nice. But it's funny to watch the videos of the people extremely scared. I don't know. It's like, it's that fine, like, what is scaring a person too much? Scaring a person a little bit is terribly enjoyable, right? But what could be too much? That might be too much.
I could say something that's almost certainly too much when people at the, I've seen several videos on TikTok and stuff of people, of amusement park workers acting like the rides aren't working and then suddenly activating them. So like those big drop things or something saying, oh, it isn't going up.
Yeah. Although maybe you pay for that as part of the excitement. All right. The next one. Well, if adding and subtracting was just the y values, what do you think you're going to do with multiplying? It's exactly the same. You just multiply the y values. But all of a sudden our mental math gets a little bit trickier. Because you could get like, oh, my one value is 1.8 and the other one's 3.7. I don't want to do that mental math. So we're going to look for strategies if we didn't have a calculator, what could make this a little bit easier. Okay? And one of the things we didn't really talk about in the previous graphs, because they sort of started at 0 and they didn't show anything behind it, is what happens when you have one graph that starts at one place and another graph that starts at a different place.
Well, with multiplication, I'd assume that well, I have two guesses. One of which is you just follow the graph that goes further than the other graph because you don't have another value to multiply it by.
Could be a possibility.
So it could just be the original graph. My other guess is because the other graph doesn't exist yet, its value would become 0, so
well, 0 would be problematic because there are values that are 0. So the best way to do it is to try to think about what you would do if you ever put in this into your calculator. 2 times does not exist.
computing error.
You're going to get an error, right? Like you could put something that doesn't exist, like 1 over 0 into this part, and then try multiplying it by 2. Does your calculator all of a sudden say, it's now okay, we're going to make it exist and be something? No. So if one graph doesn't exist, then you can't have your new graph. Adding, subtracting, multiplying, or dividing. Both graphs have to exist in order to add, subtract, multiply, or divide. So in this graph, we're going to have nothing less than 0 for our green graph. Okay, but we're going to look at some strategies here. There are certain things, mental math, that are easy for multiplying. What are your easiest multiplying ones that you can do?
I mean, one of the easiest that seem directly on this graph is 1 times -1.
Okay, so is it all right if I write that down by saying when one function is 1? If one of the functions is 1, it's going to be really easy to figure out what you do when you multiply. Because I'm pretty sure, I know you've had it holidays, but if I tested you right now, you'd be amazed how good your 1 times table still is, even after being on holidays, right? 3.5 times 1. Wow, see? Like that was even 1 decimal place, and that was super fast. So if we look on the graph, and I look on the graph, and right here, my red value is 1. Does it make sense when I times that by the blue value, it's going to be on the blue graph, exactly what the blue graph was. And here on my blue graph, my y value is 1. If I would multiply, it looks like I have my y value is 1 there. My y value on my red graph looks like it's 1.4. So my green graph would be at 1.4 right on my red graph. Does that make sense? What is the other value that's also very easy to do besides 1? Right. I'm going to write for 0. Because here, well, here both my red graph and my blue graph are 0. But here my blue graph is 0. It doesn't matter what the red graph is. It will be 0 as well. So those are nice points to be able to do multiplication with fairly easily. Other than that, you could just sort of like you could estimate, like this is going to be 3 times by maybe 1.8. What is 3 times 1.8? About 5.4. So you could 5.4. Estimate that way. You could use strategies also of, does it make sense that if you had a positive number times a negative number, you're going to get a negative number? So this part of my graph should be underneath because the red is above and the blue is below. It looks like this is what's going to happen to our graph. Again, we can do more points for mental math if we like, but we're going to get an idea from a few points. But the shape is not as easy to figure out like the adding and subtracting ones. And then the most complicated is when we divide. The basic strategy is the same. I love when the basic strategy is super easy, but things get more complicated when you divide. Like, you have certain things you're not allowed to divide by. Okay? So, I'm going to color code here. We are doing f of x is the red graph. I'm going to put a red box around that. G of x is the blue graph. So, as far as strategies go, we can't divide by 0. So, we're dividing by the blue one. I'm going to write this in blue. So if the blue graph is 0, you're going to get either an asymptote or a hole. There are the two places that it is 0. They're going to be asymptotes. Think back to chapter 2.
Excuse the interruption, but it's a very important interruption. Everyone, there is no late start in the month of January or June, so no late start tomorrow. We start school promptly at 8:30. Tomorrow we have a provincial exam for grade 12 students, about 180, very important to those students. So there'll be no 15-minute break tomorrow. You'll stay in period 2 up until 11 o'clock. Have a little extra time with your period 2 teacher to bond. And then you'll head to period 3 at 11 o'clock as the kids writing the exam will be in the cafeteria all morning. You could switch with them if you wanted, probably you don't want to. And the last thing would be there'll be no bells in the morning, so the teachers will let you switch from one class to the next. Again, be respectful around the cafeteria, around the library. When you're writing, you'll want it to be quiet. They would like it to be quiet tomorrow morning. Thank you so much, and we'll see you at 8:30 prompt.
I was questioning for a second the lack of the 15-minute break, but I guess there's no bells.
And also, they don't want, like what happens during the 15-minute break? Everybody goes to their classes and puts their head down and it's quiet for 15 minutes. That's what happens on a normal day, right? So they're worried about that excess quiet throwing the people off in the exam. Right? Just all of a sudden this hush. So if they got rid of the 15-minute break, then there'll still be a few people in the hallways and minor noises so that it should
I'm sure you wish that everyone just came and put their heads down in class promptly on the 15-minute break.
So you can't divide by 0. Usually what's going to happen is going to be an asymptote. These ones are going to be asymptotes. The only way, and if we think back to chapter 2 of when we have holes, you have a hole when a factor canceled out, right? If a factor cancels out, it would have had to be an x-intercept of the top graph and an x-intercept of the bottom graph. So if your blue graph and red graph intersected on the x-axis, you would probably get a hole in your graph. Most of the time your graphs look like this, where only the blue graph, which is on the bottom, hits an x-intercept. The red graph isn't there at the same time. So then we're going to get asymptotes. But I think there's one question somewhere in the homework. Oh yeah. Number 1, next page, 269. There's going to be one of those that have a hole in it. Okay. So can't divide by 0. So we have our asymptotes there. Right? That's one strategy. Next, think about things that are going to be easy to do. So, for example, if the red graph equals 0, what would happen? Then you would get y equals 0 over g of x. And would it matter what g of x is? 0 divided by anything is going to be 0. So that's going to be another key point. So what we're doing right now is we're trying to think of values that would be easy to divide. I mean, you can always, like, I would probably look for nice points. In this case, this point and that point are both very nice. And we're doing the red divided by the blue. What would the answer be for these y values? This y value is 1. This y value is 8. Does it make sense that that would be at 1/8? So we can just do random points if we want. But there are some other ones that are really nice to do. Another one that's really nice to do is if the bottom is 1. So right here and right here. So what happens when you divide by 1? Bet you're just as good at this after the break that you were with multiplying by 1. It's going to stay the same. So at this point, I don't even know what that x point is. It looks like my red value is 2.8. 2.8 divided by 1 would be 2.8. So this will be, green point will be on the graph. And same thing over here. That would be on the graph. And the last one that's really nice for strategy-wise, if the two graphs are the same, I'm going to label that on my graph in purple. Right here they're the same, right there they're the same. If they're the same, what do you get when you divide them? 1. So that is another point. So I can go straight down to 1 and mark a green point, straight down and mark a green. So those are some strategies you can use for dividing. Can you see that in this middle section it really looks like it's going to go up towards these asymptotes like this? Now, in the other section, on this side of the asymptote and this side of the asymptote, the blue one is negative, the red one is positive. Does it make sense that negative divided by positive or positive divided by negative is going to be a negative answer? If we estimated, I might use this point, it looks like I'm going to have 4 divided by, I have to, maybe negative 4? I'm not sure, but 4 divided by negative 4 might be negative 1. I have to do an estimate there. And because the asymptote is here, I hope you can see that this makes sense that this would go down like this. Another strategy you're going to use in dividing is looking at the shapes. What shape is the red graph? The whole thing is an absolute value, but half of it, if I just take this part, it's a straight line. If I do a line That's on the top, is fx at the top. And the blue one is a parabola. Do you see that your degree would be bigger in your denominator? What did that tell us in chapter 2? What did we have every time the degree was bigger in our denominator? An asymptote where?
Just question, dominate?
Denominator at the bottom. Thank you. So we have, like, this will be some x graph, and this will be some x squared graph. If the degree, the power, is bigger on the bottom in the denominator, we always had an asymptote. And it's okay that this point touches. Remember that this only explains what happens at extremes. So that kind of explains why this graph goes in those directions. And that is a lot more complicated than the adding and subtracting ones we started with. Like adding and subtracting graphs could have probably been like grade 5, no problem. The kids would be like, yeah, I can do that. This, a little bit more mental math, and with the asymptotes a little bit more complicated, I can see why this is more in the grade 12. So with the questions, at the end of this section, make sure you try question 1. There's going to be 1, 2, and 3. And like I said, the one graph is going to have a hole in it.